Okay? So I'm differentiating this entire thing with respect to the t. So what would be the output actually? Okay, simply this dot product. Okay. So this is equal to f of okay. I need to change t here as well. So t would be what? So v was tu, right?
So बस यहाँ पर से टी यू है जरा आपने सिर्फ टी लिखा है
कहाँ पर?
x of t है ना
ut x plus ut
ओके so ut था यहाँ
तो यहाँ पर v लिख देंगे
तो यहाँ पर सिंपली v लिख देंगे yes this is what that I'm saying actually ठीक है so I have x plus v e k x plus v e k okay dotted with e k right. So what we have calculated? We calculated d of the phi of x plus t e k with respect to dt. So this is the derivative. And now I can, replace v back by
t
and call it a ut. And then I need to do another thing. So whatever you have computed, compute it at t equal to 0. So now substitute t equal to 0. So what did you get? F of x dotted with ek. So tell me what is it?
f of x of k.
Okay, so you have the vector field f and you are dotting it with what you say ek. So this is nothing but the kth component of x. Right. Okay. Maybe what should I make? Smiley face or maybe a okay. Smiley face. Okay. So a quick review. Okay, it's not difficult. Interesting. So what did we say? So we said we have a path connected set, and let's take a point from that path connected set. And I would like to show that if on a path connected set, an open set obviously, if you have say a conservative vector field, it must be gradient. So what I did, I took a point A and on this entire, so I fixed this point A. So I can fix any point, so just fix this point A. And then on this entire U, the domain or the path connected set, I would like to define a potential for the F actually, because I need to prove that F is a gradient field. Okay? So I defined a phi from U into R, and so I'm defining it, so phi of x, I'm defining in this manner. So x is an arbitrary point in U. Now since this region is path connected, so you can always find a curve C that joins A and x actually. Okay? And I'm defining phi of x to be the integral of f over the C actually. Okay? I can find such curve because U is path connected, and this is well defined because f is conservative vector field. It just doesn't depend on the curve actually. Okay, it just depends on the points joins there. Where C is a rectifiable curve. So our claim was that f is the gradient of the phi. And then what we did, by doing a simple analysis, we showed that the kth component of f is equal to the partial derivative of the kth component of the phi actually. Okay, the rest is just proof of it actually. So, makes sense. So at least once go through it, make sure you are understanding it, practice it. There's no point of memorizing it actually, but make sure that you are understanding it actually. Okay. Then there are some physical applications. I'm not going to talk about the physical applications in this course. I'm going to talk about that in physics. Okay, since we are doing physics, so we can talk about some of the physical applications of all this stuff in physics. But one of the things that we can saw is that this gravitational field is a conservative vector field actually. Okay, we're going to see that magnetic field is a conservative vector field. Okay, they are conservative vector field. Okay. So if you wish, you can read it through. it proves law of conservation of energy. Okay, and it also talks about some of the gravitation of a Newtonian example. Like it just takes F equal to ma and defines a vector field for it. So just read it for yourself. Okay. Okay. So summary. So we say that conservative vector fields are gradient fields provided their domains are path connected. Okay. Now I would like to talk about Poincare lemma. How can I know? So, in the beginning of today's discussion, we constructed a potential for a given vector field, okay, by solving a system of differential equations, actually, partial differential equation. The question is, can I know in advance that whether my given, vector field is a gradient field or not, actually? So, without trying to construct the potential. So in other words, can I prove or can I have a result that allows me that give you a sufficient condition that if that sufficient condition is true, then your field is a gradient field. Actually, the answer is that yes, you have something what you call the Poincare lemma. Okay, so let's talk about it. I'm not going to prove it. I mean, if you wish, you can read it. The proof is optional, but it's a fun proof. Okay. Alright, so Poincare lemma. For the Poincare lemma is, for Poincare lemma, you need even a stronger condition than the path connectedness. Okay? And that stronger condition is that your set must be convex actually. This is a way stronger condition than path, because if I say, every convex region is path connected, but not every path connected region is convex actually. Okay? So convexity means that you can join the 2 points of the region, but through a line actually. Okay? Through a line. Now, and that line should entirely contain in the region actually. Okay? It's a stronger demand actually. It's a stronger demand. Can you see as compared to the path connectedness? Because it's easy to find a curve, okay, that joins the 2 points in a given region, but it would be tricky to find a line actually. Okay, so we'll see that we are going to find the plenty of examples of path connectedness. Almost every closed figure, okay, suitable closed figure is going to be path connected in Rn. But you will see that not every closed figure is convex actually. I mean, if you think that if you have this kind of a guy, this is path connected but not convex actually. Because if you take 2 endpoints, you can't find a line that entirely contains it actually. Okay. So let me define precisely what do I mean by convex field and irrotational field. Okay. Some terminology, so convex set. Okay. So I'm going to say, if I have an open set, so any open set, so it has another demand actually. So it should be open set actually. While in path connectedness, we didn't require openness. Even more stronger condition. Okay. It's important that we should talk about these things. It's important that computation is so. The way engineers do this stuff, you can learn it in maybe 1 or 2 weeks or 3 weeks. It's not a big deal. The real thing is that what we are doing is we are trying to develop the entire theory actually. And this is something that we have to be. That's the job of a mathematician. We should see that why things are true, why they are the way they are actually. Okay. Why there is something rather than nothing. That is something. Okay, so any open set U in Rn is convex if you take 2 points from the U, okay, and you join them through a line actually. So 1 minus Ta plus V for all t between 0 to 1. So that's like a convex combination actually. Okay? It's a convex, so it's a combination, it's a way to join A and B actually. Okay? And this convex combination is sitting in the U for all t actually. Okay? So this is equivalent to saying that okay, you have a region, you join them through a line, okay, and it's sitting inside basically within the region. Okay. One of the easiest example of the convex set is going to be the open interval actually. For example, you take n equal to 1, so open intervals are convex sets, which is equivalent to open ball actually. So if you take an open ball, you take an open ball, then this is a convex set. Why? Because you take any 2 points, you can join them through a line, that line entirely contains within the region actually. So these are the open intervals as well. Okay. Irrotational field, okay? So next is defining irrotational fields. Okay. You might have seen this in your previous physics course, that some of the vector fields are irrotational actually. You calculate their curl, and it turns out that they are not curling actually. They are not curl. Curl means rotation. Even it can happen that things, for example, something is flowing actually, and you don't see any rotation, but you can still find a rotation actually. Think about it. So, dariya ka pani beh raha hai, so the river is going on, the canal is going on, the water is going on, and it's just going straight actually. You're going to say, where's the curl? The answer is, there is curl. So how can I see the curl actually?
By zooming it. By zooming it out.
No. Just throw a stick in it. So would you think that the stick will go straight? It will start rotating actually. But think about it. If you have, so if I have a kind of a laminar flow actually, in which things are going faster than as compared to their, the things that are, going on boundary, and put a twig here actually, okay, so just put a, stick actually. So what are you going to say? So the metal is going faster, so it's going to push, faster. And since this part is going slower, so it will stay behind and you're going to see rotation. So even the things that are going straight, you can find curl in them. Okay? So we are talking about those vector fields or those flows are something which is not curling. So that's what is irrotational. So it's not rotational vector field. So how can I know that irrotational vector field? So field is irrotational, so here's a definition. Okay? Which is equivalent to what you have previously. We'll get to the classical notation as well, but here's the definition. So vector field F is irrotational. Okay. Physically it means that it's not rotating, something precisely uniform. Maybe, one obvious thing could be it's just constant actually, doesn't change, something like that. Anyway, vector field F is irrotational if this happens. You take the jth component of the I, F, and differentiate it with respect to the ith component, variable of the x. This should be equal to the ith component of the vector field, differentiated with the jth component of the x actually. So if you have this equality, you're going to say you have your field is irrotational vector field actually. Okay. So for example, in n equal to 3 it makes sense. N equal to 2 would be a very funny situation. So imagine I have a vector field F. Okay. How many such inequalities I need to verify? Maybe a question on combinatorics actually. How many such conditions I need to verify actually? So imagine there are n components in F. So I want to know how many equalities I need to verify.
At least one. At least one.
At least one. At least one I want exact actually.
N plus 1.
N minus 1.
N plus 1.
N plus 1.
In
Okay, so let's think about it. So let's take n equal to 3. Let's take f that is say f1, f2 and f3. Again x is x by z. So we need to do what? f1 with respect to x should be same as f1 with respect to, for example, y should be same as okay, f1, so 1 with respect to 2 should be 2 with respect to x, so that's one equality. Okay. Partial
n minus 1.
f1
N
with respect to
N factorial तो नहीं बनेगा.
who knows? Who knows? Okay. Who knows? It would be a good combinatorics question actually. But you have to keep, there must be symmetry actually. Think about it. I mean, if you replace I with j here, inequality, you still have the same equation. So you have a symmetry too. Okay. So maybe one of the interesting question could be how many equalities I need to vertically choose. For example, let's think for this. So what should I do next? So f with respect to z and f3 with respect to x, right? And okay. Obviously, I and j must be different because if I and j are equal, the both sides are the same derivative. So obviously, they are going to be equal. So we are talking about I and j different actually. Okay. So what should be the next thing? F2 say with respect to z should be same as f3 with respect to y actually. Okay. So anything else? So 3 conditions. Why 3? Okay. Why 3? Can there be anything else? Think about it. Anyway, so think about, maybe it's a good exercise to think about that. How many are going to be such a relation? No, it's not difficult. Okay? No, it's not difficult. One of the wild guess could be you need at least n square equalities. Okay? I think n square inequalities. Okay? But n square is too much. You don't have to. You don't need all these inequalities n square actually. Okay. Anyway. So understood definition actually. समझ आ गई बात? What this is. So at least in 3 dimensions you need 3 inequalities actually. Okay. So let me give you the Poincare Lemma.
2 dimension में 2 होंगे.
2 dimension में
2 होंगे.
कैसे?
Same
There will be only one.
हाँ, x होगा.
It's not straightforward.
It is only an idea.
So 3 dimension, 3 equations is accidental. It's not. It's not a kind of a. So it will be an interesting question. Anyway, so here's a Poincare Lemma. So Poincare Lemma. gives you a very interesting conclusion. It says that suppose you have a smooth vector field F. Okay, smooth vector field F defined on a convex subset of Rn, convex subset, convex set U, that is a subset of Rn. Okay. Then if F is irrotational, then F is gradient. That's it. F is gradient. Okay. So this is a long proof of it, not getting into it. It's optional for you, but I highly encourage you that at least once in your life you should do it. It's a very interesting proof. And maybe even if you want to discuss in some of the additional session, we can sit back and have a discussion about the proof, but must go through it at least. This is my suggestion. Okay, so what does this saying? So it says that if you have a smooth vector field, which is continuous and differentiable, that's what it means. And if that field is irrotational, then the irrotationality is sufficient for proving that it's a gradient field. Okay? It's a gradient field source. Here's one example. Gradient are okay. Alright, so here's a remark. Before getting into the example, I would like to give a remark. That's an important remark. Which actually talks about the converse of it. Okay? Converse of it. So imagine you have suppose you have a smooth, okay, gradient field. So you have a field that is that looks like this actually. F is gradient of phi. Then F is irrotation. Every gradient field is irrotational. This why it should be the case? Let's take a smooth vector field for this, and let's see that why it must be gradient. Irrotational actually. So for irrotationality, you have to verify this condition. Okay. So I need to take, for example, partial f by partial xj. What would be fi if you have this equality?
So gradient of phi of x.
Exactly. So this is going to be the partial f by partial xj, and that's a derivative of the partial, phi by partial xi. Okay. And it's the same as partial 2 phi by partial xi and partial xj. Okay. And I know for every gradient field, this phi must be smooth actually. So it must be a smooth scalar field. And whenever you have a smooth scalar field, or maybe a smooth map actually, then the position of the partial derivative doesn't matter actually. So if you have a smooth function actually, f of x by z, x square plus y square, smooth function, you can differentiate it, then it doesn't make difference that if you differentiate it with respect to x first and then y, or differentiated with respect to y first and then x actually. It doesn't make any difference. Then the switching of the partial order is same actually. So if this is the case, then since phi is smooth, I can say that this is going to be partial xjn, partial xi, and obviously I can rewrite xi xj, yes. So I can write that as I of the partial xj, right? And this is same as partial by partial xi of fj. Okay, so you have the equality. You have equality. This shows that the converse of, roughly the converse of this is true actually. But the converse of this statement is not true. Okay? Think about it. Because here, a longer smoothness, you need convexity of the domain as well. Okay? So you need some additional thing. So roughly you can say it's a converse of it. Converse is always valid. For the Poincare Lemma, we need to have very careful kind of a situation. Careful kind of consideration actually. Okay? Is it so if this field conservative, think about it, f of x y z is okay, so we already x square z and x square y. So we constructed a potential for it. I mean, if you remember, this is the same as the first example. Okay? But does this satisfy this? So think about it. So if the derivative of f1 with respect to y, which is going to be 2x, 2x is going to be equal to the derivative of f2 with respect to x, there must be a z here. Yes. So it's going to be 2xz, you have a 2xz. So you can see that it satisfies the condition. So it's an irrotational vector field, and what is the domain of it? What will be the domain of it actually? So the domain of this, I mean, there is no point actually which can create trouble actually. So we're going to say domain of this is entire R3.
Yes.
And R3 is by definition convex actually. Think about it. It's convex. In other words, I mean,
So
if I give you R3, so it's like an entire space, so you can take a point and take other point and you can join them the way you like it. Okay? So I have irrotational smooth field defined on a convex set, so it must be gradient. And we constructed it potential actually. So we know how to construct the potential. ठीक है मेरा भाई?
मतलब सर अगर यहाँ पे अगर फंक्शन पॉलिनोमियल है तो वो कह सकते हैं कि इर्रोटेशनल है, क्योंकि वो उसकी सर डोमेन फिर सारी वो होगी जिस पे वो फंक्शन डिफाइन होगा. जैसे पॉलिनोमियल R4 में ले रहे हैं तो वो R4 पे डिफाइन होगा हर पॉइंट पे. तो हम कह सकते हैं कि हर पॉलिनोमियल फंक्शन जो है वो इर्रोटेशनल है.
I mean, if you are taking about R4 for example, then you're going to have a map from R4 to R4.
Yes.
I mean, polynomials are smooth. They are defined on entire domains. Obviously, it's going to satisfy. They are going to be. But not every polynomial, their component should satisfy this. Obviously, ये भी है.
Yes.
सिर्फ ऐसा नहीं है कि smoothness की वजह से you get, you get it actually. हाँ, अगर वो smooth हो और conservative हो, then it's irrotational. Let's put this irrotationality condition into another kind of a framework. we'll summarize all this at the end. What we did. So you can already see what we are doing. Okay, so here's a